share your screens.
Setu 2025, an online course on space technology and applications for school teachers. Welcome to the third session of the program. It is an honor and privilege to welcome our esteemed speaker, Dr. M. Sankaran ji. Dr. M. Sankaran sir is a distinguished Indian scientist of Indian Space Research Organization and director of UR Rao Satellite Center, popularly called as URSC, located at Bengaluru, which is the lead center in the country for design, development, and realization of all satellites of ISRO. Sir is currently leading the satellite fraternity to realize various types of satellites to meet the national requirements in the areas like communication, navigation, remote sensing, meteorology, and interplanetary exploration. Shri Sankaran sir joined URSC after obtaining his master's degree in physics from Bharatidasan University in 1986. Before taking over as director URSC in June 2021, sir was functioning as deputy director and spearheading the developments in the communication and power systems area. During his 37 years of rich experience and expertise of working on more than 120 satellites, he has contributed primarily in the areas of solar arrays, power systems, satellite positioning system, and communication systems for low Earth orbit satellites, geostationary satellites, navigation satellites, and space missions like moon missions, Mars orbital mission, AstroSat, and the follow-up missions. Sir was instrumental in successful realization of unique design for power generation and distribution systems for the interplanetary missions like Chandrayaan 1 and 2, Mars orbiter mission, AstroSat. He played a significant role leading the center, achieving the historic feat of Chandrayaan 3 soft landing near the lunar south pole and Aditya L1, India's first scientific mission to study about sun. Sir is leading the center towards various prestigious space missions like human spaceflight, Gaganyaan mission, Mars landing mission, lunar sample return mission, advanced technologies for the Bharatiya Antariksh Station. Shri M. Sankaran sir is a member, fellow of Indian Society of Systems for Science and Engineering, fellow of Institution of Electronics and Telecommunication Engineers, Institute of Electrical and Electronics Engineers, and Aeronautical Society of India. Sir has been conferred with various awards like ISRO's Performance Excellence Award and ISRO's Team Excellent Awards, and has a large number of publications to his credit in the peer-reviewed journals and international conference. It is indeed our privilege to hear him today on the topics of satellites and spacecraft systems. And with this brief introduction, I welcome you, sir, to this online course for school teachers and request you to kindly deliver your session for today. I hand over the mic to you, sir.
Thank you, Dr. Meenakshi. Good morning, my dear teachers. Gives me a lot of pleasure being with you on this day to talk about the satellites and satellite systems to you, school teachers. You are the one who make the future of our country by training our children in their formative years in the schools. It's indeed my great privilege that I will be able to talk to you, and if at all I'm able to pass on some new information to you which is not already known to you, it will be my privilege. This is important because in this age of information technology, on one side, the education is becoming democratized. Everywhere, everything is available if you have access to the technology tools like a computer and an internet. Whereas this also puts the students from the less privileged schools and village at a disadvantage because of the obvious reasons. So it is the teachers like you who are going to bridge this gap between the availability and accessibility of information to students uh, that is available to city students and big schools, that has to be managed only by student teachers like you, who will act as the window to ensure that the required information reaches the student. So it is my uh, privilege that I'm able to at least give some information to you, which may not be known to you already. So with that uh, brief background, let me move on. When we say satellites, satellite systems, rockets, we all call it as uh, rocket science, as it's something that is very difficult, very distant, which is not known to many people like that. But it is not really so. Every technology is finally based upon the fundamentals of mathematics, physics, and in some cases chemistry. So as you can see in the slide, the fundamental laws which guide the placing of a satellite in orbit and making use of it are the fundamental laws which you teach to school students. These are the Kepler's laws of planetary motion and the Newton's law of universal gravitation. Whereas when we talk about the launch vehicle, the Newton's laws of motion kick in, particularly the third law of Newton, which is responsible for the design of launch vehicles, rockets. So it is important that the students understand these fundamental concepts of laws of physics, which will help the children to grow into experts in various domains in future. So it is up to us, particularly teachers like you, to impress upon the importance of understanding such fundamental laws like Kepler's laws and Newton's laws, which are even today are the basis of almost every aspect of space technology, including the satellites. Now, when we call a thing as a satellite, satellite is when the object goes around another bigger object. When you throw a stone, when you throw a projectile, the path it takes is called a trajectory. And when the trajectory becomes closed, that is, if you cannot distinguish between the start and the end point of the trajectory, and it is in a continuous motion, then it is called an orbit. If a closed trajectory is called an orbit. An orbit is what all satellites are revolving around bigger objects. For example, Moon is a natural satellite of Earth, and all our artificial satellites, what we make and if anybody else around the world makes, are the artificial satellites which are going around Earth, and in some cases Moon, Mars, and other planets, even Sun. Uh, these are the fundamental facts about the Earth, which helps us to understand how satellites work. First of all, we should know that Earth is making rotations about itself. It makes a rotation about the sun. The sun and the planetary systems make a rotation about its own galaxy center, that is the center of the Milky Way. And the Milky Way galaxy rotates about the center of the universe. This is a fundamental principle. So everything, anything which is around in this universe, they are orbiting around something. So the satellites are generally designed to orbit around the primary object. In most cases, it is the Earth. So we will concentrate a little more on the various orbits that are going to be there around there. Similar concepts are available when we are orbiting around Moon or any other planetary body. So when to understand the sizes and the speeds, you see the perimeter of the Earth is roughly about 40,000 kilometers. So when an Earth makes a rotation about itself in 24 hours, it means the Earth is having a velocity which is equivalent to about 460 meters per second, which is more than double that of a jet aircraft. It means you cannot, when you want to go around from one place to other, the Earth rotates almost twice as fast as an aircraft can go. That is why the time difference comes when you travel from one place to the other. When you travel towards the east from the west, you seem to be losing time, and you seem to be losing one day, and you land on the next day. Whereas when you are traveling towards the west, you seem to be gaining time, as if your day has got extended. This is all because of the speed of the rotation of Earth. Any object which is around a primary body is affected by various factors, including the gravitational field that is offered by the primary object. In the case of Earth, the effects of Moon and Sun, the atmospheric drag around in the atmosphere, the force that is exerted by the light that falls on from the Sun on the satellite, like this, and of course Earth's magnetic field. Like this, there are a number of factors which affect the orbit of a satellite. And we have a number of different types of orbits in the Earth orbit itself. When the orbit is circular, that is, it has a radius, and the semi-major axis is equal to the radius, then it is a circular orbit. If it is elliptical orbit, it means the orbit has a focus which is at the center of the primary body, in this case Earth, and the semi-major and the semi-minor axis are different. And similarly, when an orbit is about the poles, north and south, not exactly necessary to be at 90 degree, anywhere around the poles, plus minus. In fact, you should also know what is defined as polar region. For Earth, it is that 23.5 degrees minus 90 minus 23.5 degrees is the range for what is to be called any place on the Earth which is above 67.5 degrees is considered, plus minus 67.5 degrees is considered as the polar region. This is because Earth has a tilt of 23.5 degree about the ecliptic plane. So this means that the northernmost and southernmost points with respect to Sun can vary between plus minus 23.5. That is why Earth has a large polar region, plus minus 23.5. Whereas if you take Moon has a tilt of less than 2 degrees. So the polar region for Moon will be 88 to 92, like that. So any planet, the polar region is defined like this. Now moving on to different types of orbits which satellites use. There are two most popular orbits which till very recently have been the main orbits for placing satellites. The first one is called the Sun synchronous polar orbit. This is a low Earth orbit, which is, it means the orbit height from the surface of the Earth is less than about 1,000 kilometers. And the orbital plane is nearly about the poles, north, south, about the north and south poles. Depending on as the function of the altitude, at a specific inclination, the orbit of the satellite pulses around the Earth. So if the profession of the orbit is made to match with that of the Earth, which is 0.9856 degree per day, then it will appear that the orbit will be synchronous with the motion, relative apparent motion of the sun with respect to the earth. So this orbit is called typically for say about 500 kilometer, it is about 98.7 degree inclination is the sun synchronous polar orbit. This is an important orbit from Earth observation point of view because it means whenever a satellite in the sun synchronous orbit passes over the equatorial plane, the local time at that point remains the same every day. It means the illumination condition at that point, around that point, will remain exactly identical any time of the year, uh, except for the small variation that happens due to the sun's intensity variation that happens due to the electricity of the Earth's orbit around the sun. So this helps in imaging the same point with the same kind of illumination, so that comparison between yesterday, tomorrow, and 1 year ago is possible because it is possible to identify what is everything in the same illumination condition. The second important object is called the geosynchronous orbit. Geosynchronous orbit is an orbit which is at a height of 35,790 kilometers from the surface of Earth. At this, when you place a satellite with a zero inclination, that is along the equatorial plane, place a satellite at this height above the surface of the Earth, then its rotation matches that of the Earth's rotation about itself. It means the satellite will appear to remain stationary with respect to any object in on the surface of Earth at the equatorial plane. So this is called geosynchronous orbit. This is the primarily used orbit location to place communication satellites, for which the radio frequency line of sight between the transmitter and receiver is essential. So, yeah, all communication satellites used to be placed in the geosynchronous orbit, so that the service area is all the time visible to the satellite 24/7, 365 days a year. That this is the importance of the geosynchronous orbit. Of course, nowadays different concepts have come where communication satellites are being placed in the lower LEO orbit or even in medium Earth orbits. But even today, the most significant communication satellites are in the geosynchronous orbit. This is what I explained just a while ago. So when the inclination is zero, the orbit is said to be an equatorial orbit. If the inclination is between 0 and 90, the orbit is said to be prograde. And when the inclination is between 90 and 180, the orbit is said to be retrograde. So different types of orbits are chosen for different types of end users. So all orbits, all different types of orbits, they have their own end users which have their own unique characteristics. Now, let us talk about what is the importance of sun in using satellites and satellite-based observations. When we talk about any observation from satellite, there are two types of Earth observations that happen from satellite. One is a passive observation, other is an active observation. Generally, all Earth observations which are called as electro-optic remote sensing, they are all passive observation. It means that the satellite is not illuminating any light onto the object to observe it. It is like taking a photograph without the help of a flashlight. We are only depending upon the ambient illumination that is there in the room or the outside. The camera by itself is not illuminating the object to be imaged. This is exactly what is done in all electro-optic remote sensing satellites, where the natural light coming from the sun, which illuminates the Earth's surface, gets reflected at various frequencies and with various degrees, depending upon on what the light is incident and gets reflected back. So, when you look at the Earth from a satellite with like a camera, you will see as seen on ground. The object's properties will be seen as we see with our eyes on ground. It will be seen any object which reflects a particular color will appear that color, like we are seeing in our daily life. So from this we can the electro-optic images we can take camera like photography like images which will give real-time feel to a human brain as if we are seeing it in front of us. Whereas there is another type of remote sensing where there is illumination coming from the satellite to illuminate. We will talk about in the coming slides about that. Before we go to that, we should try to understand the electromagnetic spectrum of which we are all familiar in our schools and colleges. The electromagnetic spectrum varies right from the radio waves till to up to the gamma rays, where the wavelength from kilometer to up to 10 power minus 12, very low, very wavelengths. The interest in the electromagnetic spectrum is depending on the different wavelengths. When you illuminate any object with different wavelengths, you are able to see different feature size. For example, if you are illuminating with visible light, you are able to see like what we are seeing for naked eyes, what is visible, everything is going to be visible. Whereas if you want to see like inside our body, how the bones or other organs are there, as you know, we use X-rays. X-rays are having shorter wavelength which are able to penetrate through material, because of which we are able to see what is beneath the surface of our body, our skin. Similarly, when you use electron microscope, when you use electron as a source of illumination, we are able to see the atomic structure of the material. In similar way, for Earth observation also, various bands of the electromagnetic spectrum are used to identify and to get information about various different features that are there on the Earth to remotely see them from space. Now, as I already mentioned, the electro-optical remote sensing is mainly dependent upon the reflected light from the Earth's surface due to the illumination from sun in the visible and the near infrared region, which is used for this electro-optical remote sensing. We have microwave remote sensing. There are two types of microwave remote sensing. One is called passive remote sensing, which is sometimes called as radiometry. We are not illuminating the objects with any source from the satellite, but we are only receiving the microwaves that are naturally emitted by different objects, or the microwave that are absorbed by different objects. That is the passive remote sensing. Whereas the active remote sensing, which is generally done with microwave, is illuminating from the satellite the area to be remote sensed with electromagnetic waves, the microwaves, and get the reflected signal using the phase and the Doppler shift. The reconstruction of the surface on which the light gets reflected, that is electromagnetic wave gets reflected, brings out the data product for microwave remote sensing. Now, when we are talking about remote sensing, the most important term that is used to tell how good is remote sensing is the resolution. There are a number of different resolutions involved when we talk about remote sensing. First one is the spatial resolution. Spatial resolution is the smallest size of the object which can be distinctly seen by the instrument. That is, if you are able to see an object of say 1 meter, anything bigger than 1 meter can be distinctly seen in the remote sensing image. Then we call the spatial resolution of that instrument is 1 meter. If you are able to see object of size 1 millimeter distinctly clearly, then the spatial resolution is 1 millimeter. Similarly, there is something called spectral resolution. Spectral resolution is that from the reflected light, what is the minimum bandwidth that is distinctly seen by the remote sensed product. That is, if I am able to see within a bandwidth of say 1 nanometer or 10 nanometer or 100 nanometer electromagnetic wave, then the resolution of the remote sensed object, remote sensed product is said to have a spectral resolution of 1 nanometer or 10 nanometer or 100 nanometer. Similarly, radiometric resolution is the resolution in which the intensity of the reflected light, how small change can be effectively distinguished. That is called the radiometric resolution. Similarly, temporal resolution is the resolution of within what small time interval we are able to collect the information over particular geographic location. Like this, a number of resolutions are involved in remote sensing product. So with this, as I already mentioned, the microwave imaging, like the electro-optic imaging, is also from reflected light from the surface of Earth. Only the difference here is the light is the microwave energy that is beamed down by the spacecraft, and the backscattered electromagnetic wave is what is giving us the images. The advantage of the microwave remote sensing is that it means you can image any time of the day. That is, you are not dependent upon the availability of sunlight. You are not dependent upon cloud cover. You are not dependent upon what is the angular incidence of the sunlight on the surface which you are trying to image. So this is the fundamental uh, benefit of microwave remote sensing. Second important point is it is able to identify moisture in soil. It is able to identify different types of vegetation, the surface roughness of the soil, like we can distinguish between rock and snow and sand. It can distinguish between uh, a surface of a leaf and a tree trunk, or an object which is camouflaged or which is a natural vegetation. Like this, microwave remote sensing is able to distinguish uh, things which are not directly visible to the human eye, naked eye. Now, little more on the radar, which is the most important aspect of the microwave imaging, which is the synthetic aperture radar. First, before I go to the synthetic aperture radar, let's talk about what is radar. As you all know, it is a radio detection and ranging. There are two types of radars: non-imaging radars, which are used by traffic police for speed detection, as well as for identifying aircraft and ships by the air traffic controller or even the marine traffic control. Whereas imaging radar is a radar which takes pictures like a photograph. And this imaging radar also, there are two types of imaging radars: the real aperture radar and the synthetic aperture radar. Real aperture radar is just like a camera, where the size of the lens of the camera and its detecting element, which is a semiconductor detector in a camera, in a real aperture radar also, the size of the antenna and the, is the main thing which determines how how good is your camera. It means how fine the resolution of the camera is. When talking about radar imaging, there are two things important in this. All radars are generally looking towards the object with an angle. Generally, radars are not used to look at the object straight down. It is not nothing looking. You are not look, the radars are not made to look straight down. They are generally made to look at a side looking. That is why the real aperture radars are always generally called as SLAR, also side-looking aperture aircraft radar, airborne radar, like that they are called. Whereas the second type, which is generally used in spacecraft, is the synthetic aperture radar. To understand the radar principle, radar is nothing but a train of microwave pulses are sent at regular interval from the aircraft or the spacecraft towards the object which we are trying to image, and the reflected microwave energy is received by the radar, processed using the reference data of the transmitted microwave pulse, comparing the reflected microwave pulse for phase time, we are able to identify the size, shape, and properties of the object that has reflected the microwave energy back. So this is the basic principle of radar imaging. So it is basically working on backscattering of microwave energy from objects. Now, in the synthetic aperture, one of the main problem with the real aperture radar is the resolution along the track of the aircraft or the spacecraft is going to be very poor, because the resolution by classical methods is defined by, theoretically it is the size of the radar that will determine the resolution along the typically it will be of the order of kilometers when we are talking about the real aperture radar. Whereas kilometer size resolution is not good for any scientific or application uses. So to improve the along track resolution, the concept of synthetic aperture radar was invented. Here, the motion of the spacecraft or aircraft, the aperture, the projected aperture size on the surface of the Earth, it is falling, is synthetically enhanced to be made as a very large aperture. So typically 5 meter or 10-meter antenna can have a synthetic aperture of the order of few kilometers, 10 kilometers or 20 kilometers. Thereby, the resolution of the radar images in the along track direction can be brought down to meter and sub-meter levels. So this is the fundamental benefit of going for synthetic aperture radar. It is a highly compute intense, mathematically very intense processing of the received microwave signal, which also brings in the importance of fundamental physics and mathematics in application uses like this. Now, when a radar or even a electro-optic sensor images, it is imaged in a different way. If you want to see a very high resolution of a very small area, then you go for steering or a high resolution image, or you can, like a broom pushing over the surface completely. As the spacecraft traverses above the surface, the entire spark, entire line can be seen in the push broom. Or uh, if you have a scanning mechanism, you can go for this whisk broom kind of. So there are various types of scanning methods which are used in the remote sensing, depending upon what type of sensor is being used and what type of optics is being used. Now moving on to the communication satellites. As I mentioned, till very recently, geostationary satellites were the home of almost all communication. But today, uh, satellites in the low Earth orbits, also as constellations, are able to provide communication, including high throughput and internet services. But whatever I am going to tell here is applicable to all types of satellites which are either in low Earth orbit or in any other orbit, but mainly focused on the geostationary geosynchronous orbit. Typically, the RF spectrum used for communication is divided like this from L band to Q and V band. Different bands of microwave spectrum is earmarked by the International Telecommunication Union for various applications. For example, the L band is generally used for mobile satellite services, S band used for television broadcasting as well as mobile satellite services. C band is fixed satellite services like your Doordarshan, how they service. This is in C band, and VSAT like your rooftop antennas used in the ATMs and stock exchanges or some business houses. X band is generally used for imaging purpose for both civilian as well as military use. K band is used for fixed satellite services, broadband and intersatellite links. Q and V bands are emerging bands which are very high frequency, being currently being used only for military, but it is a potential to be used when more components are available. They have the potential to be used for communication in the civilian domain also. Now, before we get into different types of satellites and what they do, as you can see, science. When I say science, it includes mathematics. When you study mathematics, higher mathematics is nothing but physics, and when you study physics, higher physics is nothing but mathematics. So mathematics and physics are no different. They are we can call it as science only. The other important science that is used are the life sciences, which is used for biological and medical applications. Today, what we call as science, which is physics and mathematics, is pervading even the life sciences, biological and medical sciences, including uh, the genome studies also. Biotechnology is heavily influenced by physics and mathematics. And anything that we call as engineering technology is fundamentally linked to some basic science. So that is why the importance of STEM education is cannot be overemphasized. The science, engineering, mathematics, technology, these are the subjects which are connecting thread for all the types of platform that is uh, today ruling the technological domain and our lives through information technology and other compute intense technology, even including the artificial and machine learning, artificial intelligence and machine learning. So the importance of science cannot be understated. With the basic science research, the engineering is developed and the application of engineering becomes technology. When a technology is used to derive end product to an application, the user gets benefited. And by doing this end product, not only the user gets benefited, the developer of the basic science, engineering, and the application also get benefited. And now we move on to the space program of India. Before I talk about more about the space program, we should all be very proud to note that the Indian space program is the only space program around the world which was not started, which was not created to meet the requirements of the military use. Generally, all space programs around the world have been uh, brought out of the need for uh, military power, whereas the Indian space program, as envisioned by Professor Vikram Sarabhai, was born out of the vision to serve the nation, the poor people of this country. The In the early 60s, Professor Sarabhai identified the potential of space technology. If you can recall, the first satellite itself was launched in anywhere in the world in the late 1950s only by the Soviet Union. So within from 4 5 years, Professor Sarabhai could recognize the immense potential space technology has in bringing benefits to the vast masses of our country. That is how he initiated the Indian National Committee for Space Research, INCOSPAR, in 1962 itself, which subsequently was metamorphed into the Indian Space Research Organization in 1969, which we are all proud today of its achievements. So the Indian space program was basically application driven, and it was always focused on delivering benefits for the common people. Now, why a satellite? The satellite need and its unique selling points are very obvious. You can see, as you can see in the picture below Professor Sarabhai's photograph, you can see even at this distance of about 8 kilometers, you will not be able to see the surface of the earth because of the spherical nature of the earth, because earth is a near sphere, it is an oblong sphere. So the surface will go down by 5 meters even at a distance of 8 kilometers. So the curvature of the earth will make line of sight communication and line of sight imaging through uh, long distance communication very difficult through terrestrial means. The satellite offers the flexibility of able to cover nearly one third of the globe, visible globe, from a geostationary orbit, and a significant, say, about 2000 kilometer by 2000 kilometer area from a low Earth orbit. That is the main reason satellites are important, because with a single object we are able to cover a large area irrespective of the terrain conditions and irrespective of the availability of various communication tools. What you require is only electricity. That is what is required. Nothing else is required. So that is why satellite is important, particularly for a country like India, where a large section of our population lives in remote and inaccessible areas, villages. It is essential to carry the development towards these inaccessible areas. Satellite plays a very key role. And space technology is also uh, playing a big role in the UN defined 17 sustained development goals. The United Nations has identified 17 sustainable development goals, and I'm very happy to inform all of you that our space program, India's space program, is contributing to at least 13 out of these 17 SDGs as defined by in a talk maybe today or tomorrow from the director NRSC. You will hear more about this. Maybe director IIRS, when he speaks also, he will talk about it. Various aspects of how to make life more livable for the common people and how the life can be made more sustainable. The Indian space program is playing a very key role. Now coming to the satellite technology, which are the areas we are able to contribute to make it countable? Some things have been listed. Actually, the imagination only is the limitation. Our imagination of where we can use the satellite technology is the only limitation. Otherwise, satellite technology is usable in almost every walk of our life, from agriculture to science and research education, to finance and commerce to transport, logistics to energy. There is no area of development or economic activity or human development which is not touched by satellite technology. It is only our ability to imagine the application and deliver the application to the people. That only is the limitation. Otherwise, satellite technology has application in almost every conceivable societal needs. Now, one thing is to deliver some certain application, but there are certain other end users, which is also important as India grows into a more powerful and developing nation, which is going to be strong in its scientific and technical prowess. So we are looking at why space exploration is different. It is required from not only from all these application points of view which we discussed in the previous slide, it is also required from pure science point of view, because the basic human nature is curiosity. So it is required for us to know what is our universe, what is the history of the universe, how the universe has got created and evolved. Though today we have difficulty in understanding how the universe started, but the space technology is playing a leading role in making scientists understand how the universe has evolved from the time of its creation till if at all it got created. We do not know whether it was created at an instant or it was existing in a different form, but we know from beyond a point how it has evolved. It is very well known, and space technology is moving to be very vital for this understanding. Similarly, from technological point of view, it allows us to study the behavior of men and material in microgravity and radiation environment, which will help us in future to make the space as a location for high scientific activity without getting affected by the gravitational forces of Earth, and without being affected by the lack of gravity or the human physiology. All this can be made possible through scientific studies in the space. And of course, there are some philosophical significance. Those who are philosophical mind, we can look at this. It brings in the insignificance of any object that is known to us with respect to the size of the universe, and brings in the cooperation, and also makes us humble and recognize the fragility of Earth as a, as a beautiful blue bubble to be protected by us. So, uh, a number of benefits are there, not only from application and governance point of view, from science, technology, and philosophical point of view in space technology. That is why a few of these missions listed here have looked at the space as a scientific endeavor and brought in uh, very important scientific results. In this leftmost, what you see, Astrosat is the most important scientific satellite ISRO has developed and used. 10 years running, the satellite is still going strong and delivering so much of science. It is the most used Indian satellite, the most published science outcome from an Indian satellite is Astrosat. And of course, I don't need to talk about the Chandrayans and the Aditya. All of you are knowing about all these satellites. But the lesser known Exposat and the SpaceX are the game changers for the future. The Exposat is a satellite which, in the very niche area of X-ray polarization studies of binaries, that is binary stars, and SpaceX developing technologies which will allow us to have human space flight, long-term human space flight, and lunar and other planetary exploration. This has been a starting point. When we are talking about space and satellites, we cannot ignore the problem of space debris and mitigation. A number of activities are being carried out by ISRO. One of the major initiatives is that zero debris mission has been announced by ISRO a couple of years ago, which means that there won't be a non-operating object launched by India, which will remain in orbit beyond the statutorily defined period by the international community. So the international community has already defined that beyond some time, no non-functional object should be allowed to remain in space. And today, we have deorbited every one of the non-functional objects which are in space. We do not have any non-functional orbits which has outlived the time that has been specified by the international community. It is a emerging field. It's a large amount of work, mainly mathematics and computation involved. Huge amount of opportunities there in this area. And I skip this, the number of launches and satellites that India, it is all available in the internet, in the ISRO's website. It is all available. We are all proud of what we have done, but we are focused on what we need to do. When we are talking about the satellites or any space system, the most important system, most important attribute is the reliability, system reliability, because of the very nature of the space activity, which is not available for servicing. The cost is very high. The environment in which the systems have to work are very harsh. The reliability is the most predominant requirement in the design and realization of any space-borne system. So a number of demands are there on space systems, and in meeting those demands, a number of challenges are also there. And this is also one of the reasons why, in spite of the space era started more than 50 years ago, still space remains a niche area for most of the countries. And the importance of the space weather for space technology, and also space technology for the prediction of the space weather for life on Earth cannot be understated, particularly for nations which are placed close to the polar regions. The space weather plays a very important role, and satellites bring advanced warning for the space weather events for this area. And similarly, the space weather plays a major role in the design of a satellite to ensure that the satellite survives these events. Now, the satellite consists of a number of things. The purpose of the satellite is the application. The application is delivered by payload. The payload is supported by the mainframe. That is how the spacecraft is defined. So you can see here the application, which are the communication or remote sensing or navigation or any other scientific application, defines what is the payload on the satellite, and depending upon what is the payload, the mainframe systems are designed to service the payload so that the required application demanded products can be delivered. You can see that there are many items which are in the background servicing the payload. These are all important to make the payload to do its function normally. So the same thing is pictorially mentioned here. All of them together only makes a spacecraft. So details of different things we need, like home for ourselves. Structure subsystem is like a home of the satellite, where like we have our thermal blankets, or the roof and walls are protecting us from environment. The thermal subsystem protects the satellite elements from the natural elements and maintaining the temperatures of the different equipment inside the spacecraft. The propulsion systems gives us, like we have our vehicles, and with our own legs, how we get mobility. Propulsion system gives the mobility for our satellites. The spacecraft systems, the spacecraft mechanisms gives like equal to our arms and fingers, and these are opened and do different functions. These are like our limbs and arms and fingers. The power system gives the energy, like our your power supply from the grid. They provide the necessary energy for all the equipment, both the mainframe and the payload to work. The control system keeps the spacecraft in the desired orientation, orbit, and attitude. It makes the satellite behave like a well-behaved child. And the communication system acts like the ears and mouth of a human being. It hears the command from ground and executes the commands, and it also communicates it's about its own health to the ground, so that the health of the spacecraft is monitored continuously. Similarly, there are other systems like data handling systems, which collects the data from the payload system and passed on to the ground, so that the application can be built upon the data that is handled. We have sensor systems which acts like eyes and the other sensory organs of our body, like touch sense, eyes and ears. Sensor systems are there giving us the bearing of the spacecraft. Inertial systems actually are the bearing systems which identify in space what is north, south, east, west, what is the location. The inertial systems provide this information to identify. And of course, all of them put together is managed as a mission by professionals who understand the, the dynamics of objects in space and the effect of one subsystem on others. It's a very involved task. And to make all these different systems, we are assembling and integrating and testing here, overseen by the reliability and quality assurance teams. That gives a round view of how what are the different elements of a satellite. Just for the curiosity's sake, some pictures about recent satellite which was launched last year. I have put here how a satellite gets starting from a skeleton of the structure, how with the full implementation it goes through various tests, including a thermal vacuum test where the temperature excursion vacuum is simulated and the electromagnetic compatibility is verified. We verified the antenna pattern, radiation pattern of the antenna in a unique test facility, measure the mass properties of the spacecraft, and go through the vibration and acoustic test to ensure that the satellite survives the launch vibration and acoustics, then moving on for launch. Now, mission, this is for common, whatever I told till now are common for all missions, but special missions like Chandrayaan, a number of special equipments are designed, and they have to test those special equipment. A number of special tests are done. I've just given a glimpse of some of the special tests that were carried out, including a helicopter-based code test for sensor validation and crane-based propulsion testing for the Chandrayaan lander, drop test for the verifying the design of the lander. Like a number of tests are done. Here you can see early this year we have this extraordinary two small satellites of SpaceX, which is ushering in the future of our human space flight and planetary exploration by demonstrating some of the key technologies. It's a very important satellite that has been made. Now, though I am speaking from the IIRS Satellite Center, which is in the center of this slide, all our activity is in collaboration with many of our colleagues from various centers. The Space Application Center, Liquid Propulsion System Center, ISRO Industrial System Unit, and the Vikram Sarabhai Space Center, they all contribute to various subsystems and systems from payload to the composite elements. They are delivered by these systems, which are along with the URSC own realized systems, integrated and tested at URSC and made ready for launch. After the launch, depending upon the application of the satellite, the master control facility at Hassan or the ISRO tracking and command network is managing the satellite health throughout its life. And for Earth observation missions, the National Remote Sensing Center collects the data that is transmitted by the satellite to derive applications, products from the payload data. And the whole activity is supported by our spaceport, which is the SJC SHAR, for the launch of the satellite, and the launch vehicle assembly and launch happens from here. Future the future of India space program has been very vividly charted out by the government of India with a roadmap up to the year of 2047 and beyond, which involves developing a new high performance launch vehicle, very high lift, heavy lift launch vehicle, development of Bharatiya Antariksh Station, India's own space station in the lower orbit, and of course a number of Indian moon missions, ultimately leading to a crewed landing on the moon by the year 2040. Like this, in the technological and scientific domains, a large number of targets have been identified by the government of India. This, along with the our bread and butter, the daily rosy roti, which is our Earth observation, communication, and navigation satellites. We will be continuing to deliver them, of course, with the support of our industrial partners. We will be continuing to deliver and supporting the human spaceflight program, where URC is also playing a very key role in both the crew module as well as the entire service module. We will be supporting the various human spaceflight programs, starting with the Gaganyaan, which will sometime next year, we'll be, or the following year, we'll be having a crewed flight from our Indian into the lower orbit. We are all eagerly waiting for this to happen. And the maps and that is the Bharatiya Antariksh Station and the proposed the Chandrayaan follow-on missions are going to be there as a gateway for the Earth observation as well as for interplanetary missions. So, a huge amount of work has been identified for ISRO and India in the domain of space technology. And India is awaiting the children of today to come and carry forward this legacy, and to make that possible. You, my dear respected teachers, you are the ones who are going to create that future for us. To quote Albert Einstein, it is the supreme art of the teacher to awaken joy in creative expression and knowledge. This is the supreme art which you are practicing, is what is going to pave way for India as a developed nation in a reasonably short time, so that we can all be proud of our nation, and we can never underemphasize uh, the teacher's role in playing this important developmental agenda of this nation. Thank you very much for your contribution to the nation by the way of you passing on the knowledge to the young children, who in turn will become the leaders of tomorrow in not only in science and technology domains, in any other domain. Thank you very much, respected teachers, and thank you for the opportunity.
Thank you, sir. Uh, though there are many questions which have been posted on YouTube, we will not have time to take all. But if you have your permission, we can take a few questions.
Yes, yes, please go ahead.
Yeah, okay. There are some questions like one. The one Madam Tanya Kashyap, she's asking to explain the difference between the real aperture radar and the synthetic aperture radar.
The real aperture radar is the aperture size is the real size of the radar itself. Whereas the synthetic aperture radar, the aperture size is synthetically increased, say 1,000 foot, because of the motion of the satellite itself. Say, for example, if 1 second, if you take as the duration for the imaging, in 1 second, satellite can move a very large distance. The satellite, typically low Earth orbit satellite, moves at about 7.4 kilometers per second. So, aperture size is defined as the angle subtended by the radar on the surface which we are imaging. A real aperture radar is directly the angle subtended by the radar on the Earth surface. Whereas when we are talking about synthetic aperture radar, it is multiplied by the distance it is traveled along the track, the satellite, how much it has traveled along the track. So it is multiplied by roughly about 7 kilometers per second. So typical aperture of apparent aperture of a synthetic aperture radar is more than 1,000 times that of a real aperture radar.
Thank you, sir. Another question which some participants are interested to find is there any possibility in space that different type of satellites collide with each other?
It is a possibility, but the probability is quite low as of today. The probability is particularly above 1,000 kilometers. The probability is very low, but below 1,000 kilometers, that probability is very fast increasing because of the very large number of satellites that are being launched into the lower orbit, particularly in the last few years. Yes, there is a finite possibility, but the probability is still quite low.
One person he wants to know that air traffic can be monitored by satellites, but how satellite traffic is monitored? Bhasini,
Oh, I had mentioned SSA, that is uh, the space situational awareness. There is another part of that space situational awareness, that is the STA, that is space traffic awareness. So this SSA and STA happen together. Whoever is managing the collision and the debris for any space agency is the traffic manager for that space agency. Now today there is an informal international body called IADC which does this regulatory function for this, but these regulations are only recommendatory, not enforceable. That is the main reason it has no power to implement. But these are all most responsible nations and agencies voluntarily abide by these guidelines that are given by IIDC. So we can take IIDC as a traffic regulator for spacecraft.
Partha Sarthi, he wants to know in satellites, always we find something has been wrapped up with gold foil like matter. Sir, can you please explain what is that? The gold foil which is covering the satellites?
So what you see like a golden color is the multi-layer insulation that is used like a blanket around the satellite. If you know, the space temperature is about zero point 0.7 Kelvin. So any object which is exposed to that cold for a very long period without any source of heat is likely to go very cold. So to protect this satellite equipment, the satellite is wrapped with like a razai, like a blanket, multi-layer, like a razai has multiple layers of cloth and the cotton inside. The multi-layer insulation consists of a large number of aluminized kapton sheets. That aluminized kapton, aluminum is silver color, when kapton is like golden yellow. So when you aluminize that kapton, which is polyimide film, with the aluminum plating, it appears golden. That's what you see as the cover around the satellite. This is nothing like but like a blanket which we cover ourselves from protecting ourselves from cold. This is the blanket that is protecting the satellite from the very cold temperature in space.
Thank you, sir. The questions are continuing, but some are of repetitive nature. But there are many participants who are also appreciating and thanking you for the great information. Especially, I would like to quote Miss Anjali Verma. She is saying, "Thank you, Sankaran sir, for the informative and insightful session." And in conclusion, the words for teachers are really appreciable. Thank you once again, sir. So, questions, because they are repetitive in nature, I will not take more questions. Harish, do you have anything to say, or shall I offer the vote of thanks?
No, madam, you please continue.
Okay, okay. Thank you, Sankaran sir. It was indeed a very informative lecture. The way you have explained all the fundamentals, whether it was orbits or electromagnetic spectrum or type of remote sensing, the concepts of SAR, radar, some of the overview of the societal applications, about information about exploratory missions, and even up to the space debris, space subsystems, satellite subsystems, and up to the space vision, that is our Bharati Antariksh Sankaran. It was Antariksh Station. It was very, very informative and inspiring lecture from you. We are thankful for your valuable time. In spite of your very, very busy schedule, you agreed to take a session for in this school teachers program, and you have taken out time from your very busy schedule. We are really thankful to you. And on behalf of the entire SETU 2025 organizer team of IIRS and on my own behalf, I thank you once again, sir.
Thank you very much, madam.
Thank you, sir. Thank you very much, sir.